Okay, everyone, let's get ready to start the second session of the day. We're going to start with a number of online talks, and then we'll have a coffee break, and then some more talks in the afternoon. So without further ado, let's begin. I'd like to introduce Talha Siddique, who will be speaking about a cluster of machine learning-enabled magnetometer systems for online training and prediction of geomagnetic disturbances. This is an online talk, so maybe you can get connected.
Hi, can you hear me?
Yes, we can hear you. We can't see your slides just yet.
Just give me a second. Can you see it now?
Yes, yeah.
All right.
I think if you present, yeah.
Okay, so shall I begin?
Yeah, I'll give you a shout at 15 minutes, okay?
All right, thank you so much. Hello, everyone. My name is Talha Siddique, and thank you for attending my presentation. And the topic of my presentation is a cluster of machine learning-enabled magnetometer system for online training and prediction of geomagnetic disturbances. So this is the contents of my presentation. First, I'll start off with a background of what we're trying to do, our motivation behind our project, followed by the conventional forecasting steps and limitations that are in practice, generally in practice right now for predicting geomagnetic disturbances, followed by a research goal, and also this paradigm about edge machine learning, and then how we used edge machine learning as a proof of concept that we developed for our forecasting work, some preliminary experiments that we did, and last but not least, the future work. So geomagnetically induced currents are currents induced in the Earth's surface conductors, and they are caused by they're caused by geomagnetic disturbances or storms, which are disturbances in the Earth's magnetosphere caused by its interaction with CMEs or charged particles from the sun. It causes widespread malfunction of power transformers and electrical devices, and the most famous example that most of you might know is the geomagnetic storm of 1989 in Quebec, which caused a blackout for about 9 hours. So there was a recent study which showed that if a similar storm was to occur in our current technologically dependent world, then it would cause an economic loss of around $2 to $3 million. So with that in mind, there are a lot of forecasting steps present at the moment. So for example, it can be broken down into two steps. First is the monitoring using ground magnetometers or space satellites to record CME data. However, these data, such as the ground magnetometer data, they require baseline correction as well as at times temperature correction. So the current data calibration steps are not exactly in real time, because in order to get a definitive data, you at least need like 1 year of data. And the predictive models that's out there, especially in terms of machine learning, they are basically trained offline on historical data. And once the model is trained, they are deployed where it takes real-time data as input to give predictions. However, if this real-time input data falls outside the bounds of the training data set which was used, then there is a risk of failure which the model can have. And because the model is not robust to this out of the distribution input data. So this brings us to our research goal. So we are going to implement and deploy a cluster of machine learning enabled real-time magnetometer system that can first of all do real-time baseline correction of ground magnetic component and also do some calibration of solar wind data from the satellite, as well as combine this baseline corrected ground magnetic component data with real-time solar wind data from the satellites to predict rate of changes in the ground magnetic component. And the setup will ensure online training of model using calibrated real-time data, and also quantify the prediction uncertainty through a form of probability analysis. So this brings me to a paradigm called edge machine learning, which is a means of not only training the model online, but also making real-time predictions. So the first paradigm of, in order to understand the first paradigm of edge machine learning, the first thing that occurred was edge computing. So in terms of edge computing, it was basically distributed computer architectures like, say, Internet of Things gateways, which were used to process data. Then, as the hardwares got more sophisticated, we were able to deploy machine learning models on these edge devices, and this became known as edge AI. Now there's this much more focused paradigm called tiny machine learning or tiny ML, which explores the deployment and development of machine learning models specifically for compact, power efficient edge devices like microcontrollers. A microcontroller could be something like say a Raspberry Pi RP2040 or ESP32 and so forth. So, in order to do an online training, there is this form of distributed edge learning architecture called federated learning. So, the goal of a federated learning is to train a global model, which in our case is the F global, and we have m number of worker models on like n number of edge devices. So you can think of each of these edge devices as a magnetometer connected to an MCU or a single board computer. So each of these edge model units or nodes, they locally train a machine learning model, and whatever the parameters are estimated in this edge or nodes, they are forwarded to the server. And there's in the server there is the global model which aggregates these local parameters using an form of averaging scheme, and then based on that average parameter, it makes a forecast. So the advantage of such an approach, first and foremost, is it can do like online training, like right at the data source, it's training the model online as in real time instead of using like historic data. And another thing is that it basically the whole setup is it has low latency and it also consumes less power. So to test this, we developed a proof of concept, which is basically we developed a Python simulation model where we trained a CNN model in each of these nodes. So what we did was each of these nodes, we took the data from 6 different stations, which was used in the GEM challenge. And the 6 stations were ABK, NEW, OTT, PBQ, WNG, and YKC. So the reason we took this 6 is because they represent a good variability in terms of the magnetic latitude. So there are 3 of them are high latitude stations and 3 of them are mid latitude stations. So we also used solar wind data from OmniWeb, where we used the IMF components, pressure, temperature, speed, and proton density of the solar wind. So for the data, for the input variables, we use the NE and Z from Supermag and the OmniWeb SolarWind data as our input variable. And for the output variable, we use the local ground horizontal magnetic perturbation or DBH-DT as our output variable. So we took the years 2000 to 2018, where 80% was used for training and validation, and 20% was used for testing. So this is some of the like preliminary results that we have from the simulation model. We found that the model or this federated average learning architecture, it works well for certain stations over the others, but we are trying to look in like optimize the model more before we go into full-fledged deployment. So in addition to the baseline federated average, we carried out a in the server we carried out a Monte Carlo Markov chain Monte Carlo simulation in order to get like a prediction uncertainty as well. So these graphs basically represent that, where the faint blue line is the test data, the red lines is the predicted mean, and the green lines are the 95% confidence bound. So at each time step, we have a prediction for in the mean prediction, which is the red line, and with it we have its corresponding 95% confidence interval bounds. So this is basically the root mean square, normalized root mean square RMSEs for each of these stations for both the baseline federated learning model as well as the probabilistic federated learning model. So like I said earlier, like some stations perform better than the model works better for some stations over the others. And this was just a proof of concept, so that before we go for deployment, we have a basic understanding of what we can expect. So we carried out a preliminary experiment, and for the preliminary experiment, this was a preliminary deployment that we did. We focused on to see that, okay, can we get like a calibrated baseline corrected value from raw magnetometer data sets? So in order to do that, we had the RM3100 magneto-inductive sensor connected to an iBug development board. So the iBug development board is a machine learning enabled long-range wireless communication capable MCU, because it has the RAK11300 module, which consists of the RP2040 microcontroller unit, as well as it has the, like I mentioned earlier, the long-range wireless wide area network capability. So on the right, you will see the schematic diagram of the basic component that was deployed. So what we did was, the University of New Hampshire has this program called Space Weather Underground, which employs high school students to deploy fluxed-gate magnetometers, and these magnetometer data are available online in the university data repository. So we used the baseline corrected values of UNH SWAG, or the UNH fluxed-gate magnetometers, as our target variable, and whatever the raw data, the RM3100 setup that I created, that I deployed, the raw data from that is used as the input. So the idea is the raw data from my RM3100 sensor will give an output, the X, Y, and Z components, which are baseline corrected using machine learning. So first of all, I looked into the correlation between the RM3100 magnetometer as well as the SWAG fluxed-gate magnetometer. And the X components have a correlation of around 0.53, whereas the Y components have a correlation of around 0.79. And so in order to do the baseline correction for the SWAG magnetometer, so as in the fluxed-gate magnetometers, they used ALS as in asymmetrically square algorithm for the baseline correction. And in terms of the machine learning model, we used like two models. First, a distinct multivariable multivariate CNN, and the second one is a multivariable multivariate ANN. So on the graphs, you will see that on the very top row, we have the SWAG, or the fluxed-gate magnetometers X component and Y component, baseline corrected values. And on the second row, we have the real-time ANN predicted X component and the real-time ANN predicted Y component. And on the very last row, you will see the real-time CNN predicted X component followed by the real-time CNN predicted Y component. So we found that the overall it could predict the general trend, but the RM3100 had like a lot of like in a given time frame, it had a lot of fluctuations. And when we compared the real-time model over the offline model, the offline model actually performed better than the real-time model. And the reason behind this was the offline model was like trained and tested on the on a particular historical data set. But in case of the real-time one, we actually trained the model offline and then tested the model on a different day. So if we introduce the online learning mechanism, which I mentioned earlier in terms of federated learning, we expect that these results would improve. So in terms of future work, we are going to deploy magnetometer cluster or like nodes in different magnetic latitudes and longitudes, as well as implement the federated learning architecture. And given the federated learning architecture and the different magnetic latitudes and longitudes, we will also carry out like a spatial temporal analysis of whether these local data sets are IID or independent and identically distributed or not. And if not, then what are the steps we can take? So I would like to thank NSF EPSCoR for funding this project, as well as my team members from Machine Learning Algorithms and Geomagnetically Induced Currents in Alaska and New Hampshire, the Magician Group. That's it from me. Thank you. Any questions?
Great, thanks very much. That was a really interesting talk and a slight change of topic. Just wondering, do we have any questions here in the physical audience first? Yep, there's one.
Hey, thanks. That was a great talk. I was wondering how, similar to a question I asked earlier, how similar would your results be if you changed one of your magnetometers? I assume all the magnetometers used there are the same, like identical, but what if you either swapped one out for a new fancy model, or you wanted to deploy something on a magnetometer network in your favorite country or somewhere else?
That is actually a very good question. So right now, like our study focused mainly on fluxgate magnetometers and the RM3100 magnetometers, magnetoinductive sensors. So for example, in terms of the fluxgate magnetometers that we are using, the magnetometers are, the flux gates are more sensitive to temperature and requires temperature correction, but they are more sensitive and better at capturing the magnetic components. But the RM3100 sensors are not necessarily that temperature sensitive, but they are not as great as the flux gate magnetometers. So if you were to change the magnetometer, so these would be the calibration would definitely be something like what are the factors that they are more sensitive to, as well as in terms of the spatial changes. That would be something that we would have to look into depending on the magnetometering focus. Does that answer your question?
Yeah, I think so. Thank you.
Thank you.
Great. I think we have another question here in the audience.
Yeah, two quick questions. One, so pardon me if you said this. What's the sample rate on the RM3100 and the flux gates?
From the top of my head, let me just check really quickly. I mixed up the numbers.
Yeah, take your time. We're not
sorry for the trivia round here.
No, that's perfectly fine.
We have extra time, so there's no rush.
Just give me a second. I just need to look into. So thank you for your patience. And the sampling rate is 534 hertz.
For both of them?
No, for the RM3100.
Oh,
and
okay.
For the flux gates, wait, let me check the data sheet. So for the flux gates, it's around like 600 hertz.
Gotcha. And so when you're trying to sort of intercalibrate these two or match one to the other, are you downsampling the RM3100 or are you upsampling the flux gate?
So I am downsampling the RM3100 right
Okay.
now. Like in the
Have you
current-
tried downsampling it before you put it through the before you start training on it, like say like with a window average or something like that?
No, like at least for this preliminary study, we haven't done that, but this is something that we discussed for like when we put out the actual like deployment just to check. So, but for the one that I presented today, we did not do that.
Gotcha. Thank you.
Thank you.
Great. Any more questions here in the room? Doesn't look like it. Is there any questions online? No. Okay. Well, I've one last question before we go. Then
Sure.
I was wondering, in this federated learning approach, if you have stations at different longitude and latitudes which will respond differently, and then you average the results, how do you take that into account? Is that in the baseline correction or something?
Yes. So in the baseline correction process, so like I said earlier, like we are expecting that due to like the spatiotemporal difference, the data will not be IID, like as in independently and identically distributed. So there are steps in terms of like empirical risk minimizations and so forth. Like you need to tweak with the loss function of the deep learning model to make the data sets more IID. And if that occurs, then you can do the like the basic generalization or the average aggregation, or you can also like when you're doing the average or the aggregation, you can introduce a form of like a weighted average scheme, and the weights can depend on like properties such as your environmental factors or like your like the space like geographical factors like MLAT or something like that.
Okay.
Does that answer the question?
Yeah, no, it does, yeah. Great. Well, thanks very much. Let's thank the speaker once again.
Thank you.